Hello and welcome back to our discussion of ANOVA. We've been discussing completely randomized designs. If you have not looked over completely randomized designs, please pause and take a look at the previous two videos on ANOVA. Now, once we've completed designing our experiment, we then need to analyze this. Now, the reason we're doing an ANOVA is to determine if any differences exist. ANOVA, analysis of variance. So we'd like to be able to determine if there are any differences. If there are no differences, if we find no significant differences, we can stop. Otherwise, we need to find out where they are. So one thing we might ask is, what's the easiest way we might get an idea of whether or not differences exist? Well, the first thing we could do is do a box plot of our data. Now, in this case, I've got four groups, A, B, C, and D. Okay, and as we can see, here this black line represents my overall mean. This red line represents the mean for group A. The green line is the mean for group B, and then the purple line is the mean for group C, and the blue line the mean for group D. And it appears as though these means may be different. We don't know. It looks as though they're different, but we should actually test to determine. A graph like this, we would expect to find differences. However, they may or may not exist. So exactly what are we doing in an analysis of variance? Remember, we're talking about a completely randomized design. So what we want to do, remember, we've got to format our problem. So we need to set up our null and alternative hypotheses. And in our null hypothesis, what we are testing is to see if all the means equal some grand mean. In other words, do all of our means equal the total mean? So mu1 equal mu2 equal mu3 up to, notice we can have k of these different means. And do they all equal our overall mean? In our alternative hypothesis, we want to see if at least one of these pairs of means is different. Now, in order to be able to analyze this, we've got to come up with some notation. So, Yij is going to be the jth observation in group I. So we may have Y11, which would be the first observation in group 1. Y31 would be the third observation in group 1. Y14 would be the first observation in group 4. Y bar I dot, that's going to be our group means. Okay, now 4 groups, so we would have y bar 1 dot, y bar 2 dot, y bar 3 dot, y bar 4 dot, and these are defined to be 1 over the number of replications times the sum of all of the observations in that group. Okay, so here we're going from 1 to R, where R is our sample size in group I. Y bar dot dot, we're going to define that to be the overall mean of the data. Okay, so 1 over the total sample size times, here we're going to sum across the treatments and replications. In other words, we're going to add up all of our observations. We're going to divide by how many we've got in total. So N is our total sample size, and T is going to be our number of treatments. Now, the idea here in ANOVA is to compare the means by partitioning the variation in Y. In other words, what we would like to do is determine how much each observation varies from the overall mean and how much each observation varies from the individual group mean. And so in order to do this, we're going to have to define several formulas. And what we've got here, this sum across treatments and replications, okay, of Yij minus y bar dot dot quantity squared, this is going to be called our sum of squares total. Okay, this is the total variability, the total squared deviations for all of our observations. So we're taking each observation, subtracting its overall mean, and squaring it. We're going to do this for all observations. This is how much each observation varies from the overall mean. But we can actually partition this. Remember, we said we want to partition our variability. And so what we want to partition this into is treatment and error. Okay, so R, remember, that's our total number of replications in each group, times, well, here we're going to sum from I equals 1 to t of y bar I dot minus y bar dot quantity squared. What is that saying? We're going to take each group mean, subtract the overall mean from it, square it, and add them up, and then multiply all of those, that sum, by R, number of replications. And here, we're going to go across each treatment and replication. We're going to take each observation and subtract the group mean and square it. And so what is this saying? Well, this is saying take each observation in each group and subtract its group mean and square it and add them up, and do this across all of the treatments. And notice when we add up our squared treatment deviations and our squared error deviations, we get our total squared deviations. And so again, let's redefine these. Sum of squares total, how much the data varies from the overall mean. Okay. Sum of squares treatment, this is how much the group means vary from the overall mean. And then sum of squares error, this is how much each observation varies from its group mean. And these add up. And so what we have done is partition our variance into the variance because of the treatment and the variance because of the error. Now we can analyze our data by organizing it into what's called an ANOVA table. Notice we have our source of variability. There's treatment variability, error variability, and total variability. Our degrees of freedom. If you recall back when you learned about variance, that n-1 in the denominator, we called our degrees of freedom. Well, we're going to have degrees of freedom for treatment. That's going to be number of treatments minus 1. Degrees of freedom for error is going to be total number of observations minus the number of treatments. And degrees of freedom for total is going to be total number of observations minus 1. We're going to have our sum of squares treatment, our sum of squares error, and our sum of squares total. And then we're going to take these sum of squares and find out how much per degree of freedom error do we have. And that's going to be called our mean square. And so our mean square treatment is going to be the sum of squares treatment divided by its degrees of freedom. And our mean square error is going to be the sum of squares error divided by its degrees of freedom. And once we've calculated our mean square treatment, mean square error, we can then calculate our F value, which is going to be mean square treatment, mean square error. So what is F? Well, it's a signal to noise ratio. In other words, we're looking at the ratio between our treatment effect and our error effect. Now, how do we know if there's a pattern? Well, if F is less than 1, then there is no pattern because our error effect is higher than our treatment effect. If F happens to equal 1, these are equally likely, and so it's going to be very hard to see a pattern. If F is greater than 1, there could be a pattern because our treatment effect is more than our error effect, but it might be harder to see. But if F is much greater than 1, then there's definitely a pattern because our treatment effect is much more than our error effect. So we need to know how much bigger does F need to be to determine if a pattern exists. And so for this, we're going to use our F distribution, where F is distributed with numerator degrees of freedom df1 and denominator degrees of freedom df2. Remember, F is a ratio. And so it's going to have degrees of freedom in the numerator, which are our treatment degrees of freedom, t minus 1, and degrees of freedom in the denominator, which are our error degrees of freedom, n minus t. Okay, so we're going to analyze the crop data that I've put a link to at the end of this video. Now here is my crop data. Notice A, B, 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 C, 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 D, 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 and here are their yields. I'm going to create a box plot, and here it is, and it looks as though B has a higher mean than the other groups. So I'm going to create my hypothesis, my null hypothesis mu I equal mu j, my alternative hypothesis mu I doesn't equal mu j. I'm going to set alpha to be 0.1. Okay, so I need to determine degrees of freedom. Now, here I've called n, little n, my number of replications per group. In the video, I called it R. N is 4, so there are 4 replications per group. Degrees of freedom of treatment are then n minus 1. Total number of responses, n, that is going to be 16, right? In row crop. Okay, so how many responses do I have? Well, 1 to 16, I've got 16 responses. Degrees of freedom for error. Well, notice I have 4 treatments. And so degrees of freedom of error, capital N minus my treatments. So if I run this, what I'll see is that degrees of freedom of treatment, 3. Degrees of freedom of error, 12. Now I need to find my grand mean. Well, that's just the mean of my responses. And remember, my responses are the yields. So y bar dot dot, that's going to be my grand mean. And that is 7.24. Total sum of squares. Remember, this is, I'm going to go each value, subtract off the overall mean, square it, and add them up. So total number of squares here in this case, 67.84. My group mean. I'm going to take the mean of each group. So notice, there are 4 groups, there's 16 observations, there are 4 observations for each group. And so here, I'm going to take the mean of the first 4 observations. And this is my treatment A mean, y bar A dot. Y bar B dot is the mean of the second 4 observations, y bar C dot is the mean of the third 4 observations, and then y bar D dot is the mean of the last 4 observations. And so what I get for y bar A dot, 6.5425, y bar B dot, 9.555, y bar C dot, 7.035, and then y bar D dot, 5.855. Now I need to find my sum of squares. So, sum of squares treatment, remember, that's the number of replications in the group times the group mean minus the overall mean quantity squared. So here I've got y bar A dot minus y bar dot dot quantity squared, group mean for A minus total mean squared, plus B's group mean minus total mean squared, plus C's group mean minus the total mean squared, plus D's group mean minus the total mean squared. And so what I get for my sum of squares treatment, 31.22317. Now, notice I need sum of squares error. Well, we said that sum of squares total was sum of squares treatment plus sum of squares error. That means if I subtract sum of squares treatment from sum of squares total, I get sum of squares error. And so my sum of squares error is then going to be 36.62657. Now I need to find my mean squares. Mean squared treatment, we said, was sum of squares treatment divided by the treatment degrees of freedom. That means I've got a mean squared treatment value of 10.407. Mean square error, that's sum of squares error divided by degrees of freedom of error. Mean square error, 3.0522. And now I'm going to take the ratio of this. So I need to calculate my F value, which is mean square treatment over mean square error. My F value then in this case 3.409892. And so I'd like to calculate the probability that I'm greater than this particular f value. And so I'm going to use the f function, the f probability function, where notice I've got f val, that's my first value I put in, and then I've got my degrees of freedom of treatment, my numerator degrees of freedom, then my degrees of freedom in the denominator, my error degrees of freedom. And I'm calling this lower tail equals false because I'm looking for a greater than. And when I calculate this, I get 0.05309. Okay, well that walks us through the algebra, but is there an easier way to do this? And the answer is yes. We can use what's called the ANOVA function, the analysis of variance function. But notice that within this analysis of variance function, I've got an LM function. ANOVA and linear models are very closely related. And so I'm essentially nesting my linear model function inside of my ANOVA function. Now remember, with any linear model function, your response goes first. So my response is crop dollar yield, my yield values, and then I'm modeling this against my treatment. And so if I run this, what I find is here are my degrees of freedom for my treatments, my degrees of freedom for my error. My sum of squares treatment, my sum of squares error. My mean squared treatment, my mean square error. My f value, and then the probability I'm greater than that f. Now, what would this suggest? Well, remember we are testing at a value of alpha equals 0.1. Our probability, our p-value, is less than alpha, so we would reject the null hypothesis of no difference, and we would conclude that differences do exist here. Now, the next question, since we know differences exist, we need to figure out which ones. And we'll cover that in our next video. So, have a great day, and I'll see you next time.